Hello everyone, welcome to this session. So in this session we will be talking about how you can analyze your Amazon Aurora and RDS data in Amazon Redshift with zero-ETL. My name is Sudipto Das. I am a senior principal engineer working on Amazon Redshift.
And my name is Jignesh Shah. I'm a director of engineering in the Aurora and the RDS team. And I'll give Sudipto the first way to start with it, and I'll come back later. Thank you.
Thank you. So in this world today, data is your differentiator. There are many studies by various analyst firms that show that more and more data is being created every day. More than 90% of the data has been created in the last 2 years itself. Another study shows that you are 8.5 times more likely to increase your revenue by 20% if you are able to leverage this data that is being generated around you. But only 32% of the organizations today are able to leverage this data and use it for its competitive advantage. As more and more of these enterprises and companies are moving to use data as a competitive advantage, they rely on near real-time analytics, whether it is applications such as personalizing their users' behavior of their app on their website, fraud detection in near real time, inventory optimization, customer relationship management, you name it. In all of these application scenarios, what you really care about having access to insights in near real time and be able to act on those insights so that you can optimize your business. Deriving these insights requires you to build complex ETL pipelines where you spend a lot of energy in these ETL pipelines, which takes time away from your business logic. And this is why AWS has been in this journey for the past several years, investing on this zero-ETL future, where you can focus on your business logic and getting near real-time analytics, while AWS takes care of connecting your different types of data so that you can derive these insights. So in this talk, I will focus very specifically about a few of these different sources and the analytics engine. AWS has built its purpose-built operational databases in Amazon RDS and Aurora, and its analytics solution in Amazon Redshift, which I'll provide a brief overview of. Then we'll cover zero-ETL in action to show how zero-ETL simplifies your life in getting these near real-time insights. We will cover some of the recent launches that are tied to zero-ETL in the Aurora and RDS set of services. And we'll end this talk providing some of the underpinnings by getting deep into how we actually pull this off so that you can get an overview of what is going on behind the scenes and how it works and why it works so well. As many of you are familiar, Amazon RDS for open source engine has been a premier database offering for more than a decade now. It makes it easy to set up, operate, and scale open source database engines such as MySQL, Postgres, and MariaDB. It's fully managed from a deployment, security, patching, availability standpoint. It's cost effective so that you don't have to rely on expensive commercial licensing. It takes care of high availability with options such as 3AZ, so that you can tolerate different types of failures, including even an AZ going out. And one of the primary focus points of RDS is compatibility with open source, having access to both the latest major as well as the minor versions, and providing an easy way to migrate either your on-premise or your self-managed open source solutions into an AWS managed solution. In this relational database family, we also have Amazon Aurora, which is our purpose-built database, relational database that provides unparalleled high performance and availability at a global scale, while providing the same compatibility with open source software such as MySQL and Postgres. Aurora provides up to 5 times higher throughput compared to standard MySQL and 3 times higher throughput compared to open source Postgres. It can scale out to up to 15 replicas. It has a decoupled storage and compute that provides high availability as well as many nines of durability across with the data replicated across 3 different availability zones. It is built from the ground up to be secure, providing encryption at various levels, and is also fully managed, including a serverless offering that as of this year also scales down to 0, that also takes care of your scaling characteristics as your workload changes dynamically. Hundreds of thousands of customers use RDS and Aurora today. One statistic here is that Aurora is used by 955 out of the top 1,000 AWS customers, and you'll see many familiar names here. So we have this, many of you are using these purpose-built operational databases to run your applications and your operational portfolio. On the analytics side, AWS offers Amazon Redshift, which is a fully managed AI-powered cloud data warehousing solution. It allows you to bring your different types of data from transactional, clickstream, IoT, streaming, application logs, and etc. into one place where you can use rich SQL, machine learning capabilities, data sharing, etc. to analyze your data and derive rich insights from the data. It allows you to connect to the different set of tools to provide visualization, machine learning use cases, as well as generative AI use cases. And it also has many built-in intelligence capabilities using machine learning itself to tune its resources, to tune the database system, so that again, from your perspective, you are spending more time on deriving insights rather than managing the service. One of the key value propositions of Amazon Redshift is its industry-leading price performance. So this is what we hear from our customers, that they really they care about price and they want their system to be performant. So on the left-hand side, you'll see this is an industry standard benchmark based on the Transaction Processing Council, the TPC-DS benchmark, which shows Amazon Redshift, which is the bar in green, as you compare with other competing cloud data warehouse offerings. In this figure, lower is better, which means that you are getting better price for performance, the lower the bar is. As you can see from this figure, compared to our alternative cloud database data warehouse providers, Amazon Redshift is up to 3x better price performance when you are sequentially running queries, one query at a time. But most of our real workloads are concurrent. When you have BI dashboards, there are many concurrent users that are driving these dashboards. And in the case of these concurrent workloads, your price performance advantage increases even further, where you can get up to 7x better price performance. Tens of thousands of customers today use Redshift for driving their critical business insights. You have many familiar names here, and along with the Amazon.com business, which also heavily relies on Amazon Redshift for deriving the insights. Now you have these purpose-built databases. You have the operational databases on one hand, where your drive, which is the source of the data, where all of your operational and your transactional data is generated, and you have your analytical system on the other end, which derives these powerful analytics. And if you want to derive these analytics, connecting these requires you to build complex pipelines. How many of you have built such pipelines in your day-to-day job? Looks like many of you. How many of you enjoy building these pipelines? I didn't see any raised hands. So this is where a lot of the energy, that's what we hear from our customer, where they spend a lot of energy not only building these pipelines, where it's time consuming, but it's also maintaining this pipeline as these different changes happen. So you start with your high performance transactional systems, for example, RDS or Aurora. You have your analytics system, and then you define the custom logic, which changes from one system to another system, and every customer is replicating it, and managing it becomes a challenge. With zero-ETL, we want to replace it with a very simple and easy setup so that this becomes easy for you to get started. So some of the key benefits of zero-ETL are, we want to make it incredibly easy to set up and manage. So you should be able to get started with zero-ETL in the matter of minutes compared to weeks and months that many customers spend today building these ETL pipelines. The other aspect is to provide you near real-time access to your data in the matter of seconds from when the data is committed on your operational database to when it's available for your analytics, while making sure that the transfer is completely secure using state-of-the-art encryption techniques both during transit as well as in storage. So this way you can rely on the data being securely transferred, your business data, critical data being securely transferred between the two systems so that you can use it for your analytics and machine learning use cases. Another aspect of zero-ETL is that you may have various different operational sources. You may have multiple different databases, you may have other sources from streaming, etc. And we want to be able to consolidate this data into one warehouse so that you can derive global insights from across your application footprint. And this also plays into the overall analytics strategy and journey that AWS is after. Right? As you may have seen with some of the announcements from yesterday, where AWS is reimagining how the overall analytics journey becomes. At the core of it is this lakehouse. Here we have Amazon Redshift, which powers a big chunk of this lakehouse, and the data gets stored in the Amazon Redshift managed storage. You can have various different data sources. Here I am listing only a few of them. Like you can have the data coming in from files in S3. Amazon Redshift provides a service called a feature called autocopy that automatically copies your files from S3 into Redshift. You could have streaming ingestion from your Kinesis or Kafka instances. You could have zero-ETL. What in this talk we are covering Aurora, where we already support Aurora Postgres and Aurora MySQL. You could have from Amazon RDS. We have support for Amazon RDS MySQL. You could also have the data coming from Amazon DynamoDB. And all of these zero-ETL integrations and these features are generally available, allowing you to consolidate your data and bring it into Redshift. Once it is in Redshift, with some of these announcements that we made yesterday about the SageMaker Lakehouse, we make this data visible to your Lakehouse catalog so that you get an easy and consistent way of discovering this data from your Lakehouse catalog, as well as defining consistent governance policies so that your most significant business sensitive data has the right access control policies set up. And once it is in this Lakehouse, you can have your familiar set of tools for analyzing as well as transforming, curating, cleaning, and learning from that data. So we have support and integrations with Amazon EMR, Glue, Athena, QuickSight, SageMaker, to name a few. And with the SageMaker Lakehouse announcement, you will see that this entire slew of services can now access this data once you have used zero-ETL to move this data into this analytics system. So with this, I'll hand it over to my colleague to show you zero-ETL in action, and I'll come back with some of the deep dive later on.
Thanks, Sudipta. Let's look at the zero-ETL in action. I'll be talking very specifically about the relational databases, zero-ETL. If you have experience building your own data pipelines, you understand that it's a major task, right? You have to understand various different services, understand how to kind of pipe the data from one service to another. Then you have to prototype it and implement those pipelines. Building the pipeline is actually one part of it. What we traditionally understand is you then have to spend a lot of time handling all the edge cases of the transformation that you do, and make sure that you handle all the cases, which could take weeks or months. So with zero-ETL, it helps you to set up all this undifferentiated heavy lifting behind the scenes and get your pipeline set up in minutes. This actually gives you a very easy way to start very quickly. And on top of that, it actually gives you a wizard to help you set up and fix the things that you need behind the scenes to make it work. So the way you can create an integration is use the CLI or the console. I recommend the console because as part of the console experience, you get a fix it for me. And the way the fix it for me works is you look at the source database, set up, it gives you options to say, hey, these parameters are not set up for you, and it would enable and give you an option to enable those parameters on your source databases. For example, if you're using MySQL, it will help you change the bin log format to row, which would be needed for zero-ETL. If you're using one of the Aurora engines, it will help you set up the enhanced bin log for them and enable it. Similar thing it would do even for the Redshift side of it. It will help you set up the encryption needed for Redshift to make the zero-ETL work. It would even help you set up the case sensitivity parameter that would be needed to make it work. The fix it for me also helps you to say, hey, do you want to reboot and make those parameters live so you can start the integration, and you can select whether it's now would be the right time to reboot those instances or not. This actually simplifies your experience to a degree that it's just point and click, make the setup, and you are ready to go, right? Once the parameters and the integrations are set up, an integration behind the scene is created for you, and while creating out there, it will make sure that the parameters are correctly set up for you and everything is working. And when it gets out there, it goes into an active state. When you see an active state, that means the integration is created behind the scene, but it's not ready to use yet. In order for you to use the integration, you then go to Redshift and you have to define the database name for your integration. You could do that in a two-way, either use the console to create the name, or you could use the CLI in Redshift to say create database from the integration ID that you just created. Once you do this step, you don't have to babysit this integration anymore. The data will now be flowing behind the scene. To see how we achieve this continuous data flow integration, let's look what happens behind the scene for you at that point of time. When you first create that Redshift database integration out there, what it will do is it would set up the initial load behind the scene, which for the purpose of the slides, I'm going to call it like the seed data. The seed data is the current state of your source database that it will move in a large batch to the Redshift. Once and the way it would happen, it doesn't really care about like how many tables you have, how many schemas you have. You have an option to kind of pick during your setup what things you want to replicate. It could be hundreds of tables, and once you have that, it would start replicating them. The requirements are typically like you need like a primary key to allow it to be replicated, but it may happen that some of the tables don't have primary key. The console gives you an easy way to see all your tables that are missing those primary keys, so you could take action for them if you want to continue replicating to them. Next, what you want to also understand is like, when you move data as part of your columns and the attributes, how are the data types handled? Now, for example, if you're using Aurora Postgres, the Postgres data types and Redshift data types are quite similar, so they would move pretty with the same, majority of the common data types would move as is out there. However, if you're using Aurora MySQL or RDS MySQL, you may need to understand how the data types are converted when it moves to Redshift. So for example, if you have a varchar in your MySQL engines, it would actually move as varchar in Redshift too. But if you have, say, integer or float or date time type of data types, they get converted to their equivalent data types in Redshift. And there is a long list of data types that are supported. So in this QR code that you have, it takes you to all the data types that are automatically handled as part of the integration of that. I recommend you to kind of like keep on checking that page, because we keep updating it as more and more data types are added out there. Next, once your initial set of data is moved, it doesn't mean that you have to stop your operations on your source database. While the move is happening, nothing prevents you from taking changes on your source databases. The reason for that is like the way it's designed. Once it moves into the initial set of data, it will automatically switch to a change data capture. And it keeps track on where to start that change data capture, and it would then automatically switch to CDC behind the scenes. With CDC, it will continue to capture all your changes that are happening on your source database and replicate that onto the Redshift side. Now, as you know, you could do schema operations which could impact the state of the table and the indexes and other things. They are moved along with it. So with the zero-ETL, more than 80 plus data modification type of languages and DDL would be handled seamlessly out here for you. So for example, I'll show an example on how this would work. So you create a new table with a primary key. Within few seconds, it would show up on Redshift. If you modify those rows and update them, within few seconds, it will show up in Redshift. You could even delete rows, then the rows would be deleted in Redshift. If you add rows, or you could add more rows and hundreds of thousands of rows, they would show up in Redshift in a few seconds. Typical expectation would be about in 15 to 20 seconds, all data is available in Redshift. When you do large deletes, it would be deleting on the other side. You're not preventing just the data. You could even delete column, and within few seconds, the same columns would be deleted from Redshift. So you could make those modifications, and you don't have to kind of make those schema in sync on the other side. It automatically handles that for you. So for example, you add a new column on your source database, you would see that new column up there. End of it, all your schema changes are automatically replicated on Redshift. But typically, it's not just the schema that could be changing on your database. You could be having your database configuration changes out there that's going behind the scenes for you. Zero-ETL automatically handles all configuration changes which are common, like the reboot of the database failover, the database port configuration, that changes that you do on the source side. It automatically handles and adapts to it and keeps on replicating it for you. Similar thing, you could be making changes on your Redshift side. Zero-ETL understands all those changes and automatically adapts to all the changes that are happening on the Red side. Our goal out there is to make sure that the changes are handled automatically behind the scenes without you needing to do any extra work to keep track of the changes. There could be scenarios. End of the day, these are based on the open source technologies like MySQL and Postgres. There could be edge cases out there which could break replication for you. In such scenarios, zero-ETL will automatically detect that the replication has failed for a specific table, and it would resync or reset that entire table and get back to a continuous data flow out there. So there is a monitoring that always happens, and if the replication for some reason breaks, it would create like a sync again and restart from that point onwards. This actually greatly helps out in cases of handling unknown cases that can happen and can break your application, and automatically handle that. So you don't have to do like a manual intervention to kind of like fix that for you. So with that, the goal is to transparently always stay in sync with your source database. Once the zero-ETL integration happens, the data is expected to be in sync. But I want to talk about what are the design priorities that we have done while designing the zero-ETL. If you look on the transformation that happens, we focus on security as the utmost priority out there. So in zero-ETL, all transmissions are happening with security in transit as well as with data at rest, which is one of the reasons like the fix it for me at the beginning make sure that the encryption is enabled everywhere. Next, the priority is given to data correctness, which means whatever is transferred is transactionally consistent view and always correct. So it keeps monitoring that and make sure that it's always accurate in the replication. On top of that, we focus on reliability. Reliability is more related to like breaking changes that are happening behind the scenes for you and be able to automatically adapt to that. So that was like the third priority that we used while designing the zero-ETL. And then make sure that there is a minimum performance impact to the source database. We leverage multiple strategies in order to make sure that the impact on your source database for transforming that data to Redshift is minimal. And at the end of it, what we also do is improve the speed of that transformation to Redshift at the fastest possible speed that's possible with the current stack that is being used. So once the data is in Redshift, you can now use all the features that Redshift provides. You could use the materialized views, further transform the data, export the data to S3 for your data lake. You could use machine language features. You could also do like archival cases. One of the popular cases would be to kind of like move your non-hot data from your OLTP to your data warehouse and remove that from your source database. Those things are now possible using zero-ETL. Once the data is in Redshift, it gives you more controls on how you want to handle that. Zero-ETL feature also gives you more monitoring capabilities. So for the way, if you are familiar with CloudWatch metrics already, all the metrics related to zero-ETL are available in your CloudWatch. The type of metrics available is like the number of tables replicated, the replica lag, the data transferred, and even the current state, if you want up there. With zero-ETL, on your Redshift side, you also get the system views that you could actually do like a query to understand the state of your application using like an SVV integration table, which gives you the status, and you could go deeper into the table state and get real-time information about the data that is transferred. With that, the next thing I want to jump is into recent developments that has been released. Compared to last year when Aurora MySQL Zero integration was already available, we have now expanded it to like 31 regions, added data filtering as a new feature as part of that enhancements that we have done. We have even added the cloud formation support through APIs, improved the getting started experience with the improvements in Fix It For Me related to this engine, and also added event triggers that you could do for checking on subscribing to events like altering the database or drop columns and other things, so you could take more actions along with it. There is a JSON data type support that was also added, which expands the number of data types that are supported. Just a couple of months ago, we also announced the zero-ETL integration of Aurora Postgres to Redshift in a GA mode, which means you can now use it for production use cases. Compared to what was earlier available in preview, the GA release now supports multiple databases that could be defined on your Aurora Postgres to be moved to the Redshift with a single integration. It adds support for schema changes that you can do on your Postgres databases, and they would be automatically replicated to Redshift with those things out there. And it also supports logical replication slots. If you have that, they could be moved. It uses logical replication to move all the databases on the other side. Like all the logical databases will be replicated into its individual databases on Redshift. So that's like the improvements that are available with Postgres. Continuing on that, if you are using the pure open source versions like MySQL, the MySQL zero-ETL integration is also now GA. Similar thing, it is expanded to like 21 regions as part of the original preview. Table filtering is now available with it, similar with the CloudFormation. So we have expanded not only just for the Aurora engines, but we are also expanding it to RDS. With that, I'll probably spend like a few minutes on the new features that were released, which is like the data filtering. So the data filtering is now supported both for Aurora MySQL, Aurora Postgres, as well as RDS MySQL. Now, one of the things you need to be aware about, like the slight differences between the MySQL engines and the Postgres. In MySQL, a database and a schema are synonymous. So they would typically, the data filtering uses like a star.star format. So it's basically a schema.table type of filtering. And the data filtering gives you both options. You could say, here's my expression to include for zero-ETL, or here's my expression to exclude out there. So you could do the combinations to select which one gets replicated to Redshift. On the Postgres side, because you have logical databases on that same Postgres instance, it uses a database.schema.table. But like I mentioned, a single integration can support multiple logical databases, which means all the logical databases that you want to replicate, you would add them out here. You could say, database 1.star.star, which is like include all the schema and tables related to database 1, will be replicated automatically. If you want to add more and more databases, you can just add and include them out there. They will be automatically transferred to Redshift. Each Postgres database will show up as a separate integration. You select a different database on the Redshift side, and they will be automatically handled for you. The next thing I want to talk about is like the performance improvements that we have done on the Aurora engines. In order for that to explain that out, I'm going to talk first about like how the RDS MySQL bin log replication works. So traditionally, if you have used bin log replication to replicate a MySQL database, it creates an information about all your transactions. And if you go deeper into that transaction view, you would see the way it would do that is like, first of all, MySQL will make all the transactions. When you're ready to commit, it would then start writing into the binary, the bin log file. And once the bin log file has all the changes, that's when it would commit the transactions. So that way it gets like a consistent view of that. This is slightly inefficient because when you're ready to commit, you're waiting for writing the bin log records out there. So on the Aurora Postgres, Aurora MySQL, as part of the enhanced binary log, what we do is we actually start the writes along with the transactions as they're happening in memory. And when it comes to the commit state, it is actually, the writes are pretty much done by that point of time. And when you commit, it actually results in a much faster replication to Redshift. This work was actually done primarily to kind of like speed up the data movement from Aurora to Postgres. This actually helps us to kind of like achieve the 1.4 million transactions per minute support in zero-ETL. I mean, it makes it like pretty fast to get you all your data in Redshift to be visible. Similar changes have been done also on the Aurora Postgres enhanced logical replication. Get to improvements. Additional improvement that has been done in the Aurora Postgres logical replication is to handle the common DDL type of changes to make sure all your schema changes are also reflecting on your Redshift side. So that has been an additional improvement. That's how you're getting all your handling of your columns and the schema changes that you're doing on Postgres to reflect back in Redshift. With this, end of the day, what really matters is how real customers use it and give their feedback back to us, right? And I'm happy to see, the feedback that we hear from customers like Infosys and Intuit is a pleasant experience one. If you look through that codes, what you would find is it kind of reiterates on how zero-ETL helps them to spend less time on the undifferentiated data plumbing work behind the scenes that happens, so that they can actually focus their work more onto getting the faster data decision that they need to do based on the data that they have. With this, I think I'm going to give Sudipto the power back to take us another level deeper on the magic that happens behind it. Thanks.
So Jignesh gave you an overview of some of this high-level usability as well as the performance characteristics. So one of the numbers that you saw was supporting millions of transactions per second on your operational database in Aurora, and the data getting replicated in a matter of seconds into Redshift, so that you can get near real-time analytics from Redshift. So a lot of engineering went behind the scenes in order for us to be able to achieve that kind of performance, be cost effective, and one of the more important things is the impact on your operational database is as minimal as possible, so that your operational traffic doesn't get impacted as we are doing this zero-ETL replication behind the scenes. So one of the aspects that we covered was this concept of seeding, that when you set up a zero-ETL integration, you want your data to be moved from your operational database into your analytics optimized storage. Here we have RDS MySQL, where a typical setup where you have writer instances and reader instances. If you were to do it by yourself, you would typically either read from the reader instance or the writer instance. If you're reading from the reader instance, you have to worry about the transactional consistency, the lags, and so on and so forth. And if you're going to the writer instance, there is the possibility of impacting your workload. When you're transferring hundreds of gigabytes to terabytes of data from these operational databases, that can be a significant impact. So in order to minimize this impact, in the case of RDS MySQL, when the zero-ETL integrations are seeding, behind the scenes, we use this concept of a snapshot to create a clone, so that it gets a transactionally consistent snapshot. The clone is then used to export the data into a storage, so that it can be replicated to Amazon Redshift with as minimal impact as possible on your writer instance. With Aurora, we have taken a step further, because Aurora has been purpose-built with Amazon's technology, where we have innovated in decoupling the compute from the storage. We were able to take it even further. So in this setup, what you are seeing is that there is a writer instance, there is a reader instance, and there is the decoupled the storage layer of Aurora. When you initiate a zero-ETL integration, again, what we are relying on the ability to create fast clones, so that we can get the metadata corresponding to that data even from the clone without ever impacting your primary database instance. And then we use the shared storage layer, which is spread across many storage servers, to be able to, in parallel, export that data out of the storage tier without ever touching your compute tier. As a result, not only is that more efficient and low impact on your operational database, it is also up to 10x faster than what we can offer with RDS MySQL. So even if you have databases of the order of terabytes that you are setting up zero-ETL integration, the integration can seed in a matter of tens of minutes. That allows you to, again, get to your analytics faster. Once you are done with seeding, the next step is how do you keep up with all these changes? As I said, your operational database may be running hundreds of thousands to millions of transactions per minute, and we are relying on this ability to capture the CDC stream and then replicate it on Redshift. Again, if you are doing it by yourself, you would capture the logical replication stream from your head node. If it's in the case of MySQL, it would be binlog. In the case of Postgres, it would be Postgres logical replication. As some of you may be aware, it comes at a cost. It comes at resources being contended from the operational database. It has a latency impact on your transactions, and these are critical resources taken away from your operational database. So instead of reading in from the head node, in the case of Aurora, again we rely on this decoupled storage to be able to perform this CDC streaming. What we do is that as transactions are executing, and while we are writing the data and committing the data in storage, in parallel we write this logical log records into another storage volume, which we call streaming server, which is again in parallel decoding these log records, understanding whether these are data manipulation operations or schema changes with DDLs, etc. And in a streaming fashion, they are processing this data and handing it over to Redshift so that they can be applied to Redshift. Again, because this happens at the storage layer, there is minimal impact on your transactional workload that is executing on the writer instance. This CDC replication has been built both for Aurora Postgres as well as Aurora MySQL, and as Jignesh covered, in the case of Postgres, we have also enhanced the logical replication compared to standard Postgres logical replication to even be able to replicate DDL. Now, as this data is moving over to Redshift, another aspect is how do you lay it out in Redshift, right? And how do you make sure that Redshift can efficiently ingest this CDC stream and apply those changes so that they become queryable, again in the matter of seconds from when the transaction committed on your operational database. So behind the scenes, we rely on the fact that if you are familiar with Redshift, Redshift is a massively parallel processing architecture where there is a leader node and there are a set of compute nodes. There are various cluster configurations that are supported. So we rely on this parallelism that is built into Redshift, and we pre-partition the data that is moving in from Aurora into Redshift based on the data characteristics. We support, behind the scenes, we support various different sharding policies. For example, either we can replicate the entire data by itself, we could do a primary key based sharding, Redshift topology, and this automatically detect based on the workload pattern as well as the data distribution, so that you can move the data efficiently with minimal CPU overhead on the Redshift side and optimizing the replication lag as well as the resources consumed to replicate. Now, as this is how the underlying replication works. There is another set of tricks that we have implemented that allows you to get efficient analytics on it. And here I'll walk you through how does this lightweight concurrency control and the recovery mechanisms work on the Redshift side that allows you fast access to that data so that you can drive your near real-time analytics. So what I'm showing is a schematic of how this table from the operational database gets represented in Redshift. A table will have a primary key, then there will be these additional columns which will be the actual values, and then we use the underlying multi-version concurrency control mechanism of Redshift as well as knowledge of transactions on the source side to provide these transactional snapshots that you can use for your queries to provide the correct results on your analytics. Here you will see we are internally tracking several columns such as xmin and xmax. If you are familiar with Postgres' multi-version concurrency control, this is how Postgres tracks what versions of data is visible and which versions of data is not visible. In addition to that, we are also tracking the LSN from the source system, and that allows us to give a transactionally consistent prefix so that as the data is getting replicated, you are getting your analytics query results as of a prefix of your LSNs. So let me walk you through an example. So let us say we have two keys, A and B, that are written on the operational database, and they are now getting replicated onto onto Redshift's representation. As you can see, these two keys got the Redshift's transaction ID of 100. This is the transaction ID that was used to apply the CDC stream, and we are also carrying forward the LSN or the log sequence number that came in from the operational database into here. Now these two changes were applied on the Redshift side, and assume there is a query, an analytics query here depicted by T1, a transaction T1 that started operating on this data. So Redshift uses its own multi-version concurrency control to get a consistent snapshot of this data. So while this transaction is active, they will only see these two tuples and no other tuples that get added to the table. While this transaction T1 is active, assume that more changes are happening on your operational database, which is again getting replicated. In this case, the row C got added, which got a Redshift transaction ID of 200 and the Aurora LSN of 3, for example. And similarly, another row got added, again with Redshift transaction ID of 300 and LSN of 4. As you can see here, because Redshift got a transactional snapshot, even though transaction T1 might still be executing while this replication is happening, that transaction doesn't see that data, so that we get a consistent snapshot. In order for us to be able to make this data, the new data that came in, visible to newer transactions, we came up with an optimization, what we call is an in-memory commit. So as the data gets applied and an Aurora transaction commit is seen, we perform an in-memory commit, which is pretty cheap in Redshift. Once this data is committed in memory, it becomes visible to subsequent transactions. So even though on the Redshift side the data may not have made it to Redshift storage, in memory we are making the data available to new queries. So if a new query T2 starts executing, at this point in time they will see the rows C and D as part of their transaction snapshot and be able to run on newer data to provide fresher insights on your data. Now you may imagine what happens here, you only committed in memory, what happens if there is a failure in this case? We rely on the aspect that Aurora has already committed and persisted that data, and our CDC stream itself has a way to replay that in the event of a failure of Redshift. So if, for example, in the case where these rows C and D were committed in memory, and after that there was some reason there was a failure in Redshift and Redshift restarted, we will be able to remember what was the last state that was committed on the Redshift side on Redshift storage, and from there we will be able to replay the stream. So in this case we will detect that C and D did not make it to the disk. So as part of Redshift's recovery mechanism, Redshift will reapply them and make sure that your data is always available and there is no worries of correctness. So in this case, after recovery, as newer CDC elements come in this case E, then C and D are applied, and then E is applied, and then subsequent transactions can use that tuple. Another very important aspect of replication of CDC is that change data capture means data is changing, it's not just inserts, but there are also updates and deletes. And if you are familiar with any analytics systems, these analytics systems, in order to be efficient for the reads, they are not optimized for these updates. They are optimized for inserts. But updates are very common in OLTP workloads. So in order to be able to support a steady stream of update and a high throughput of updates, we came up with another innovation where we use a concept of a delete buffer to track any updates or deletes. So what we do is, whenever we detect an update in a CDC stream, we break it down into a delete followed by an insert. We stored the delete separately, we buffer them again in memory. We apply the inserts on the primary table, and there is a hidden delete buffer that is maintained, that now when you are querying the data, our query scan operator is intelligent enough to be able to stitch these two data tuples together to give you the impression as if the data was updated without the update actually being applied as an update statement. So let me walk you through an example here. We have again our example of ABC. A transaction started, ABC got the snapshot, so it views ABC. Now assume there was an update on the source side where the key A was updated. What you will see here is that update got broken down into a delete. We inserted an entry into the delete buffer with an LSN of 300, which is the transaction at which this delete was applied. And then we also inserted the new value into the primary table with an LSN of 4 and an insert LSN of LSN of 300 and an insert LSN of 4. So this basically shows that the previous value of A has now a visibility from 100 to 300, and the new value of A has a visibility of LSN 300 and higher. So if a new transaction now starts on the Redshift side, what it will do is that it will be able to combine these two data items as well as the xmin and xmax context that we stored to be able to read the new value of 4 as if it was applied as an update on the Redshift side. Similarly, if data tuples get deleted, for example, C got deleted here, it only gets added to the delete buffer. D got inserted, it only gets added to the insert buffer, and transactions just automatically see this because our scan operator is now intelligent enough to handle that. And this is one of the critical innovations that allowed us to sustain this high CDC throughput while making sure that we can provide a single digit second of lag or from your operational data to your analytics. Now, if you notice, this cost of combining these two is slightly more expensive. We are spending a few additional CPU cycles, so we don't want to keep doing that. So occasionally what we do is that we have a background vacuum process that takes this delete buffer and actually clean it up so that it persists this data into the base table. So after this background vacuum or the compaction process runs, you will see that the data got updated in place. So subsequently queries don't have to keep paying the cost of merging this. But because this happens asynchronously in the background, opportunistically across the system, your transactions don't see an impact of that. And after the compaction, you get back to your optimal performance. So with this, I will conclude this talk to recap some of the key takeaways for you. We presented the zero-ETL integrations that allows you to focus on your innovations so that it is easy for you to set up and manage and get started, bringing these pipeline setup from of the order of weeks and months to the order of minutes. We want to provide you with secure near real-time analytics so that your most business sensitive data you have the assurance that it is transferred between the systems with highest form of security. And by combining data from different sources, you can now derive global insights out of your data. As I mentioned earlier, there are various different zero-ETL sources that we support. So in this example, what you will see is that in a single Redshift data warehouse, you can bring in data from RDS MySQL, not just one, but multiple clusters of RDS MySQL. You can bring in data from Aurora MySQL compatible or Postgres compatible. You can bring in data from DynamoDB. So if you have your different operational databases, you can have all of this data come into a single data warehouse in Redshift so that you can derive analytics across your different operational portfolio. And it's not just Redshift's SQL analytics. You can use the power of the other analytics services that AWS provides to derive the insights that are needed for your use case, whether it's Spark, whether it's SageMaker, whether it's Trino, whether it's Bedrock, QuickSight, so on and so forth. And this basically plays into our overall analytics strategy that we are after to give you analytics on all your data for all of your users. Once you bring in the data into Redshift, you can use Redshift's own set of scaling mechanisms using serverless. You can create a data mesh. Redshift supports access with its own managed data as well as data in your data lake. You can bring in data from the various sources. Yesterday, we even announced zero-ETL from 8 different SaaS providers. So you can bring in data from Salesforce, SAP, and so on, again into Redshift. And with the SageMaker Lakehouse announcement, once the data is in Redshift, you can expose it to your analytics tool or your machine learning tool of choice using an Iceberg compatible API. So with this zero-ETL journey, it's not just bringing the data into Redshift, it's a matter of enabling it for your broader analytics journey so that as the data starts from your operational sources into the life cycle of machine learning, you can have this seamless data transition go through its entire journey. So we have been investing in this overall zero-ETL vision that we laid out many years back. Every year, we have been enhancing these zero-ETL, not just with sources, but also with newer features, as we talked about, so that you can perform analytics on your transactional and operational data without building complex data pipelines. And it frees up your team so that you focus on your application use cases and getting insights out of your data and accelerate your AWS cloud data strategy and journey so that you can drive better decisions for your business. Give it a try and keep the feedback flow coming to us so that we can keep improving this overall set of features as well as our set of zero-ETL sources that we support. And with that, I'd like to thank you all for your time and for attending this session. And please take time to complete the survey for this session on your mobile app so that we also know what other things we can improve in the presentations. Thank you very much.